All right. Yesterday, I wanted to start analyzing this set because it makes the easier transition into the StatEs as we're going to talk about it. So, null alternative hypothesis. Really, the way that I think it's nice to see error analysis is this. In a court of law here in the United States, you are innocent until there's enough evidence to say that you are not innocent. We call that guilty. So I'm going to write not innocent, which we do call guilty. And I challenged you guys in class yesterday. I said, hey, what are the two mistakes that can happen? And you guys said, well, you could be innocent but be convicted, which would be bad. And you could also be guilty, but there not be enough evidence, so they're going to let you go free. Do we agree that those are the two kind of errors? Okay. So the easiest way to help kind of set this up is I kind of make a box. And if you print up your notes, I think the box is on your notes. Yeah. It's pretty easy to draw the box like this. And here's what I kind of want to paint the picture of, which is this is what happens in reality. And we kind of don't know what that is. In reality, in a court of law, we don't really know if you're innocent or guilty. Only you kind of know that answer, right? But remember, you're on trial, so you're not going to if you are guilty, you're not going to self-incriminate. But then you're going to go to the lawyers, the judges, and they're going to debate it. And in terms of statistics, we're going to take a sample and analyze that sample and make a prediction about what that reality is. So these are really conclusions. And I'll say conclusions based on evidence. And in terms of statistics, that's fantastic. Statistics is what that was. In terms of statistics, we should coin that word. Statistics? I don't know. Anyway.
Statistics. I'm an AP statistics.
We don't speak good in AP statistics.
We're in math, not AP.
But we know how to do math gooder.
We math good.
We math good. Conclusions based on evidence again. Conclusions based on evidence will always be worded in this way, especially in statistics, and it does relate to the court of law. We will either fail to reject the null hypothesis, and that's the wording we're going to use in the language, or we will reject the null hypothesis. And when we reject the null hypothesis, that's a good thing. Consider that we're saying that there's enough evidence for that. And these are the only two outcomes that I can have. And I'm going to even erase this. And so I'll move that up. Okay? And then in reality, we don't really know this. Did I provide on your guys' notes, was it actually printed up for the box?
Yes.
Okay, so you want, is it okay if I flip-flop that so it matches your notes? It's going to be better for you guys? Because it doesn't really matter in the whole scheme of things, but I would at least kind of like to parallel your notes. Reject the null. And this is, and if you already have it the other way, you can keep it, yeah. It doesn't really matter. We just got to make sure everything matches up. So, again, reject the null hypothesis, which is to say there's enough evidence, or fail to reject, which is, again, saying there's not enough evidence. In reality, we can have two things happen, and I'm going to write H, the null hypothesis is true, which in the context of this situation, the reality is you are innocent. Does that make sense? And the other thing that can happen in reality, and remember, we don't really know that, because that's what we're looking for the evidence as, is the null hypothesis is false. So, in context of this problem, if in reality the null hypothesis is false, which that means in reality you are what? Guilty. Then we would hope that there would be enough evidence to convict you, which would be the conclusion of, remember, here's your evidence and conclusion. That means you would reject the null hypothesis. So I'm going to kind of put a smiley face right there. Not necessarily for you, but kind of, if we are citizens of this nation, that's what we want to have happen. The criminal is in reality guilty, and we say there's enough evidence to convict them. Does that match up in terms of context? The other thing that we kind of like to have happen is, if in reality you are innocent, we would really like the court to say, fail to reject the null hypothesis. There's not enough evidence to say you're guilty. Good, because I'm innocent. You should not have enough evidence to say that I'm guilty. Does that make sense? Okay? And again, the language that we use is fail to reject. There's just not enough evidence. And I'll put another happy face there. Oh, good, I can't. Pirate, apparently. This criminal got beat up. He was getting set up.
I thought he was innocent. So
Yeah. I can't draw gooder.
Draw gooder. Could be more than that.
And now, it should be evident that these are our errors. In reality, you're innocent, but we rejected the null hypothesis. We said there was enough evidence to say you were guilty. Does that make sense? Okay? This error right here is called a type 1 error. Okay? Now, remember yesterday we talked about the significance level. I labeled it alpha. Remember that? The significance level, the alpha level. Okay? Alpha level is the probability of making a type 1 error. So I'll say that again. Your significance level on our hypothesis tests, we get to define it. An alpha level of 0.05 means 5%, or on average, 5% of the time, in the context of this problem, we will send an innocent person to prison. That's a little rough and dark. So do we agree? Do we see that connection of alpha and significance level to where it fits in the context of this problem and where it fits in the context of the overall scale of things? The other error we can have, and you guys talked about this yesterday also, we call it a type 2 error. A type 2 error is when in reality the null hypothesis is wrong, which is guilty, but we say there's not enough evidence to say you're guilty. Okay? We call that error, it's a beta error. We abbreviate it by the Greek letter B. It's a beta error. So again, that's alpha, beta. Vocab, you might want to make vocab cards on this stuff, because I'm going to give you another piece of vocabulary. That box right there that I have in red, that's power. Okay? Okay? And beta over here that I talked about, beta, oops, I can't draw that. Beta is level is the probability of making a type 2 error. Does that make sense? Alpha, probability of a type 1 error. Beta, probability of a type 2 error. Just a vocabulary word here. Here's that power piece of that power definition, because it's hard for students to see. When I'm looking at the situations when the null hypothesis is false, these are the situations where the null hypothesis is false. And those are the two outcomes that can happen. Agreed? Again, in reality, I'm guilty. Two things can happen is say there's enough evidence or there's not enough evidence. Okay? Power is the probability of rejecting a false null hypothesis. Okay? I'll write that down again. Oops. I got to rescale this thing. Power is the probability of rejecting a false null hypothesis. And these two probabilities, beta, which is type 2 error, and power, are complementary. So power, I think I did it in red, is 1 minus beta. Okay? Power is 1 minus beta. Okay? The last vocabulary word. That's, let's see, I'll put that in maybe green. Right here. If it's 5% significance level, wasn't our conclusion 95% confidence? Yes? And did I say yesterday the relationship between confidence and significance level is 95 to 5, 99 to 1, 90 to 10. So this box, which is in reality the null hypothesis is true, and we say there's not enough evidence to reject, that's confidence. Okay. That's confidence. That's a type 1 error. That's power. That's a type 2 error. These are things that are tricky. The vocabulary and what goes where is hard because the expectation is what you're going to be able to do from today forward is when I ask you to analyze these errors in context. I want you to define them and then make a judgment about it. Does that make sense? Because the catch is, and this is kind of connecting it all together, as statisticians, in a perfect world, my alpha error and my beta error would both be 0. Does that make sense? In a perfect world, that would be great. We don't live in a perfect world. Because of that, we have errors that exist. And statistically, we can control for one of these errors. And that's the catch. Do we agree that over here with confidence intervals and alpha levels, I can choose an alpha level of 0.1, which is 10%, 0.05, which is 5%, or 0.01, which is 1%. That's 99% confidence, or 95% confidence, or 90% confidence. Do we agree that I can choose those and control that? Yes. Here's the deal. Mr. Wood, why don't we just go with 99% confidence every time here? Okay, we can do that. Let's put that into context of this problem. If we want this to be 99% confidence, we don't want to have that error happen very often. That means, let's see, we're going to limit this error. The null hypothesis, you're innocent, and we're going to reject the null hypothesis. We've said we don't want to send any innocent people to prison. So we're cranking this up. We can crank it up to 99.9 if we wanted to. Okay? If we crank this error up, we don't want that error to ever happen, or we're going to control for it as much as we can. Minimize that error. We're not going to send innocent people to prison, which is, in reality, you're innocent, but we said there was evidence against you. When we tighten up and control for our alpha error, our probability of a type 2 error increases. Okay, I'll say it again. When we control for this error, and we want to see this happen, when we control for this error, which says we're never going to send any innocent people to prison, this is what we're concerned about in America, then the type 2 error will increase. If no innocent people are going to prison, we will then be letting more guilty people go free. So we can't control for both of those at the same time. As one goes up, the other will go down. Does that make sense? If we live in some different society and we're going to say, you know what? We don't need to have that much evidence to convict you. If we don't need that much evidence to convict you, our type 2 error will be very small. But that means we're going to send a lot more innocent people to prison, and our type 1 error will increase. I call it the teeter-totter effect. Does that make sense? Seeing that relationship is huge in error analysis. I guarantee you, you will see some component of error analysis on your AP free response. And I guarantee you will see at least one of your 40 multiple choice questions about this. And we'll revisit it again. It's a big deal statistically. Okay? All right. That doesn't have context. I don't really care. I'm going to do this one. Here we go. This one has context. And I want you guys to do that. I know it's small handwriting, so I'll read it. If you have printed up notes, it's on there. Water samples are taken from water used for cooling as being discharged from a power plant into a river. It has been determined that as long as the mean temperature discharge of the discharged water is at most F, there should be a number in there. Is there a number on your notes? What is it? 150? Is at most 150 degrees Fahrenheit. I just have a typo there. At most 150 degrees Fahrenheit, there will be no negative effects on the river's ecosystem. To investigate whether the plant is in compliance with regulations that prohibit the mean discharge of water temperature, 50 water samples will be taken or will be randomly selected, and the temperature of each sample will be recorded. So what I want you to do in the context of this problem right now, identify the null and alternative hypothesis. Again, I'll read you the keys. It has been determined that as long as the mean temperature of the discharged water is at most 150 degrees Fahrenheit, there will be no negative effects on the river ecosystem. So you need to write down the null and alternative hypothesis right now. I'll give you guys a tip. It's going to start like this. Oh, I'll give you another tip. There you go. Just a second. How many people so far so good?
Yeah.
All right. Yeah, if you have either the equal sign or this, those are both equally correct. And I will take both for full credit. Now, students will commonly put less than 150 here. Okay, so I want to be clear about that. What would we like to demonstrate? We want to test whether they're doing it right or not. Remember, our alternative hypothesis is the only thing we can have evidence for. If I want to demonstrate that they're doing it wrong, then I want to look for evidence of greater than 150. Can I test for compliance if I get a null hypothesis where it's less than 150? It's just whatever. I can't prove that you're doing it wrong. What's that? We want to prove they're doing it wrong. Yeah. You could prove that you're doing it right, but I think in the context of this problem, it says there will be no negative effects to investigate whether the plant is in compliance with regulations. So you should be looking for evidence of them not in compliance. Contextually here, that's what good as a conclusion. If we test for less than 150, I think it's 150. If we test for less than 150, I don't know that we're going to prove anything. We haven't proved they're doing anything wrong. I mean, we have evidence to say that they're doing it right, I guess. So one of the things I would probably look at is, what's my sample mean? In other words, if I have these 50 samples, I might do one-bar stats and see if it's greater than or less than 150. And if it's less than 150, I might switch that hypothesis. Does that make sense? It was kind of like a pretty extended thought, but. All right. Describe the type 1 error. I want to challenge you guys to do that right now. Not only do I want you to tell me what type 1 error is, describe it in context. In other words, link what we just talked about to the context of this problem, and then describe a type 2 error, link it to the context of this problem. And the third part, which one of those errors is more serious and why? Okay, and that's the kind of critical thought we're looking for. She's not here today. Or do you want me to give it to you? It's for your significant other. Who is it? Who is it?
Wow.
That's not the right question to ask, I don't think, my friend.
Wait till she hears about that response, Brendan.
I think I'll text her right now.
I can text her, I have her number.
Who? What's one?
Brandon's a player.
All right, let's go ahead and do these problems.
Player.
Oops, forgot that was recorded. Doesn't matter. The type 1 error is rejecting the null. Where'd it go? Oh man, I got all that slides back here. Type 1 error. Rejecting the null hypothesis when in reality the null hypothesis is true. So in the context of this problem, where's my slide? In the context of this problem, this is in reality true. But your samples led you to the conclusion of that. Does that make sense? So we'd say there was evidence to say that it was more than, 150 degrees Fahrenheit. In reality, it actually is not less than 100. It actually is less than 150 degrees Fahrenheit. That make sense?
So when we say that second.
So what? Number 2, are you guys ready for number 2's answer? Or do you guys want me to restate number 1?
Restate number 1.
Okay, restating number 1. The type 1 error is rejecting the null when in reality the null hypothesis is true. Okay? So that says we reach a conclusion. When we reach a conclusion, that's having evidence. We have evidence to say that the temperature is greater than 150 degrees. In reality, the water temperature is not greater than 150 degrees. Okay? That's a type 1 error in context. Taking it a step further, you don't need to write this, but taking it a step further, it means these 50 samples of water that we got actually average to greater than 150 degrees. I just happen to get some pretty rare samples. Does that make sense? Okay? Yes.
Did you want the context in the, like let's say that was on the test, describe a type 1 error, would you want the context there?
Yes.
So, type 1, what would you say?
We'd want to say a type 1 error is the probability of rejecting the probability of rejecting the null hypothesis when in reality the null hypothesis is true. In this case, it means we conclude or say that there's evidence that the water temperature is greater than 150 degrees, but in reality, it's less than 150 degrees.
It's that second part that you want.
Well, both.
Or both.
Both. I want you to show me that you know the definition of a type 1 error, and then I want you to apply the definition of type 1 error in context.
So you don't merge those.
You can merge them if you'd like. If you can get a sentence where it does combine them, that's fine. But what I'm looking for, and like as an AP grader, what I'm looking for is you demonstrate that you know what a type 1 error is, and the only way you can demonstrate that you know what a type 1 error is to tell me what it is, and then apply it correctly in context. Does that make sense? So almost 2 parts or 2 sentences.
So those are 2 requirements.
Yeah. Type 2. Hopefully you got type 2. Type 2 is failing to reject when in reality the null hypothesis is false. So we say there's not enough evidence to conclude this, but in reality that's true. In other words, in reality the temperature coming out is greater than 150 degrees, but we said there was not enough evidence to conclude that. And then the third part that I expect you guys to do, what type of error would you guys at this point consider to be more dangerous and why? What do you think? Type 2 error? Because the reality is if you make a type 2 error, that means that that water is actually hot and it's destroying the ecosystem. Does that make sense? And that's a bigger error in the context of this problem, I would say, because if you make a type 1 error, it just means you're going to shut the plant down or something like that because you say it's too hot. Does that make sense? Because you guys agree that the repercussions here, if it's too hot of water, they're going to have to shut the plant down and they're going to fix whatever's broken. Okay? So really, when we're talking about what type of error do you think is more serious, it kind of depends on who you are. If you're the people who are working at that power plant, do you want to be shut down? No, because you lose money if you get shut down. Especially if you get shut down when you're not supposed to get shut down. So if I'm the owner of that company, then the type 1 error is more serious because I lose money. But if I'm the person who's trying to find out if they're polluting the rivers and damaging the ecosystem, and I'm the environmentalist, then the type 2 error is much more serious.
So the probability is not serious.
We will, most of the times, this one's ambiguous on purpose because I want to demonstrate that it kind of depends on who you are. If I'm owning this and they make this error, I'm shut down and I don't get to make money. If I'm the environmentalist and this happens, it's destroying the ecosystem even though there wasn't evidence to say it was destroying the ecosystem. So purposely ambiguous. In AP exams and most of your homework, it'll be specific because we'll start getting into say something like a pregnancy test. Okay? What about type 1 and type 2 errors in a pregnancy test? Would you rather be not pregnant and say you're pregnant, or would you rather be say you're not pregnant but in reality you are pregnant? Well, you can make a judgment there because if it tells you you're pregnant, you're probably going to do some things that aren't risky to your health. But if you get something that says you're not pregnant but in reality you are, you might do riskier behavior to yourself. So, do you see what I'm saying? Like that gets to the gray area of risk. And that's really, when we look at drug testing, cancer testing, all of this risk assessment comes down to that alpha beta error, really. And which one is greater for the greater good. And it ties back into those ideas. If you remember a while back, we talked about false positives, lung cancer, and smoking, non-smoking, and stuff like that. So it does relate. This is just a small snapshot. All right. That's kind of it for errors. I do want to do a couple more. That's from a while ago. Or at least from this time, a couple. Okay. All do you have two? How many did you want me to have?
I wanted you to have a dozen.
Okay.
What are you doing?
I pulled a lot more of my hair out if I had more than two.
I can see for put all your kids in the bucket.
My wife and I said we only wanted two because when we die, we're going to exit two, and we'd like to do two on Earth. If we wanted more kids, we'd adopt. I told you we're lame. When you marry a math teacher, lots of lame stuff happens. She did? That's awesome. You guys going in Christmas?
No, it's gonna be Christmas
They blow snow. Like real snow. All right. Kind of talked about this earlier. This is a visual. Hopefully it'll help you out. A upper tail test. Oh, wait. An upper tail test, we're testing for evidence that it's greater than. One-sided to the right. Greater than. A lower tail test, we're looking for evidence that it's less than. A two-tailed test, and again I'll kind of less than, greater than, and a two-tailed test is not equal to, and it really doesn't matter what side they're wrong on. Really the two-tailed test is saying, well, my buddy said that most people watch an average of 3.2 hours of television a night. I'm going to say, no, I think you're wrong. Go and sample them, and I don't really care if there's more than 3.2 or less than 3.2. I just care that it's not 3.2. Does that make sense for your two-tailed test? Yes? Okay. And for the lower-tailed and the upper-tailed, more than 3.2 hours of television watched or less than 3.2 hours of television watched. Okay. These are the same 8 steps as yesterday. I'm not going to go over them because we're going to do a problem. We're going to do our second one top to bottom today. Yes? 10.2. 10.2, 10.3, I think.
It's 10.3.
10.3?
It's the next day.
It's the next day now. Go back.
Yeah. Thank you.
All right, same 8 steps. As yesterday, you will get them memorized. That's a small problem. I'll read it out loud for you for those of us who didn't put up the notes, and then we will do it top to bottom. You are concerned that a majority of smokers do not view themselves as being at increased risk of heart disease or cancer. Because of this, the authors call for a public health campaign to educate smokers about the associated risks. In support of this recommendation, the authors offered the results of a study of 737 current smokers selected at random from U.S. households with telephones. Of the 737 smokers surveyed, 295 indicated that they believed that they had a higher than average risk of cancer. Does this data suggest that P, the true proportion of smokers who view themselves at increased risk of cancer, is in fact less than 0.5, because they claim half, less than 0.5 is less than half, as claimed by the authors of the paper. Use a significance level of 0.05. So, 8 steps. The first 4 are pretty specific and pretty straightforward. Number 1, define what it is you're talking about. Is this a proportion or is this a mean? Proportion. So it's a capital P. In this case, what's the context of our population? P represents the true proportion of what? Smokers who view themselves as being at increased risk. You should see, well, this last test that you guys took is probably one of the most writing intensive tests you guys have taken, I think. Right. But as far as writing sentences, you guys have written a lot on the probability stuff, but it was very mathy. This was probably the most written.
Ready?
It's Friday. I can't talk good today.
It's well.
I figured I
talk-
was doing that.
I talk badder and badder. Yes, I did do that on purpose.
You sound like Miss Collins.
She's very punny. She can't pronounce people's last names correctly. Yeah. Clinton. There's most students in school think Mr. Clinton's last name is Clinton.
I know. It's
No thanks to call in.
I know.
All right.
she got Rican last name,
He's like, yeah.
right? She called.
Special.
I
Okay.
called how
Miss Colin? Okay.
Enrique I say.
Or Colin.
Yeah, that goes well.
Using
All right. Null hypothesis. What's null hypothesis here? Don't all jump at once on this. That's correct. That's what this is. And what is the null hypothesis?
That increase cancer risk is
equals
0.5.
whatever that thing is.
Is less than 0.5.
We'd like to look for,
Yeah, is it?
in fact, less. You want me to make this less than or equal to?
No.
What are we looking for proof of?
Greater than.
Does this data suggest that P, the true proportion of smokers who view themselves as being at increased risk of cancer, is in fact less than 0.5? So we'd like to see if the authors are what? Correct or incorrect?
So greater than. I don't know. It's not saying.
Well, yeah, it's one of those. What does it want? Can I scroll up a little bit?
What?
What do we want to be for our alternative hypothesis?
Greater.
Oh, you want it to be greater than 0.5. No, 'cause that's what they're looking for. They're looking for like it's less than.
Does this data
It is.
suggest that P is less than 0.5?
Greater than.
Less.
Wow, it took me a second.
Is this what you were talking about?
Yeah, okay.
Then we agree.
I wasn't here
It is said to test us at the 5% significance level. There are steps 1 through 4. You should be comfortable with that. When you entered class, you should have been able to go those steps 1 through 4. Last night's homework was based on that with a little bit of error analysis. If you were somebody that had issues with error analysis, our discussion today should clarify those issues. You can go back and do those problems. Step 5. Identify what you're doing and justify why you're doing what you're doing. This is a one proportion Z test. And we must verify or talk about or justify 3 things: independent, random, and normality. So, normality. Is the sample significantly large? Can we apply the central limit theorem? What constitutes significantly large in one proportion? N times P greater than or equal to 10. N times 1 minus P greater than or equal to 10. So in this case, bless you, 295 out of 737. So 737 times 295 over 737 greater than or equal to 10. Yes. 737 times 1 minus 295 over 737. And that is also greater than or equal to 10. So sample is significantly large. So the central limit theorem is applicable or is applied.
Well, they said CO3 if you have to set the limit there.
Write it out. Here's the way it takes. Why I say that? It takes 5 seconds to write it out instead of writing CLT. Don't give anybody who's grading your exam an excuse to take off a point. All right, sample certificate. God.
Yeah, I think we should stop this lesson because I'm not getting anything.
I'm not getting.
The way you're talking is.
What else? Random. Does it talk about randomness in the context here? Smokers were selected at random from U.S. households with a telephone. So we'll say, cite that you read it and can understand it. Smokers were selected at random. Did I not say something right here? From U.S. households with telephones.
Should we spell out United States?
I think you're fine with spelling out the United States. Again, the reason I say central limit theorem, that directly applies to statistics. I think it's safe to say that most people understand that the abbreviation US stands for the United States.
Selected from us.
Selected from us?
Yeah, look at get the dot. Get the dot. Do you remember?
You're part of the experiment right now. You're actually in somebody else's reality. You're a dream within a dream.
Inception.
And you're part of the matrix. So really, I'm just binary coding right here.
Oh, snap.
Make sure you eat the, what is it, red pill? Blue pill. What pill is right? Is it the blue pill? I don't remember. I'm just happy I got that much connected. Matrix, binary coding, and Inception. Is it red?
Oh, Inception.
They have pills.
No, they have pills in the Matrix.
Oh, okay. I was like.
And you need to get out of the Matrix because the Matrix is the computer keeping you like, yeah, when you're reborn as a human, get out of the Matrix. But Inception is like a dream within a dream.
Yeah,
within a
yeah.
dream.
That's what I was thinking.
What I did was I took something from the Matrix and I applied it to Inception, implying that you might be able to get out of your dream if you knew that you were in a dream in Inception like you did in the Matrix. All in 10 seconds. What you want, Matrix 1 or Matrix? Oh, well, I tripped some kids up. You know, at the end of the Inception, he had that little spinny thing that was on, not weighted correctly, but it spins. And that's the catch. It didn't, it started wiggling, so you don't know if it fell or not. And then I told one of the kids when that movie was out, I'm like, you know that keeps spinning at the end of the movie, and the kid was tripping. He's like, it keeps spinning? Wait a minute. I just,
No, that had me like, freaking, I hate the ending of that movie. I'm like, is it gonna fall? I was like, it's spinning.
It's on purpose.
It's wobbling.
Now I forgot.
Let's watch that movie.
Well, he had a little top that he was supposed to take with him all the time, so he could always test if he was in a dream or not. And at the end of the movie, he spins it, and if it wobbled, he was in reality. But if it keeps spinning, he was in a dream. I can't remember which
If
one
it
it was.
stops.
If it stopped, okay. If it fell, because it wasn't weighted right or something like that, and then at the end of the movie, he spins it, and it starts to wobble, but it doesn't show you if it keeps spinning or if it falls.
Oh, yeah.
So you don't know what's
You're
what.
really missing out.
So, yeah, the first time I watched that movie, I was confused.
What's that?
The first time I watched that movie, I was confused.
Confused.
So I watched it again.
All right. We do need to finish this problem up before class ends today. Smokers were selected at random. What's the other thing we need? Independence. Less than 10%. Is there more than 7,370 smokers in the United States? Yeah. So I'll say reasonable to assume sample is less than 10% of the U.S. smoking population. Okay. Next, that's kind of the nuts and bolts. You've got to justify why you're doing what you're doing. It will always be independent, random, and normal. Now we're looking at a z. That's going to be p hat minus capital P over the square root of p times 1 minus p over n.
This is 6, right? It's still 5?
This is 6. Now, one thing students do, they don't know in this z statistic which p part to use down here, p hat or p. You use the p from your hypothesis test, okay? In this case, it's 0.5. Students will sometimes try to put their p hat statistic down here. Does that make sense? You actually put your p hat statistic down there when you're doing the confidence interval. The one you just did, that was the p hat statistic. And this calculation, you use the p from your hypothesis test. We have to use the p hat from our sample, though. And I forget what that number was, 295 over 737. Yeah, it's 40%. And that's all you need for that. Do say what that z-score is. Go ahead and calculate that. What'd you guys get for z-scores there? Negative 5.4? Negative 5.414? 413?
What? I got 4.
All right. Now I'm going to ask this question. This sample, this is connection pieces. I hypothesized that it was 0.5. I hypothesized that in my bucket Gatorade bottle, 50% of the population believed themselves at increased risk. I sampled from that population, and I got a sample that said 40%. Our conclusion, and it should support it, we are 5 standard deviations away from normal if 0.5 is correct. Does that make sense? So in fact, we would say there's strong evidence to say that that 0.5 is incorrect. Does that make sense? Because if the 0.5 is correct, me getting this sample from that 0.5 population is statistically, if I could say it, 0. Right? Does that make sense? In fact, the probability of me reaching in and getting a sample that rare will be norm CDF negative 10 comma negative 5.413 or negative 100 comma negative 5.43. Which, by the way, real quick, plug it in. What do you get?
3 times 10 to the negative
3 times 10 to the negative 8, which pretty much is. Do we agree that's strong evidence? Okay. All right. I'll finish this up in just a second.
Wait, real fast. Plugging in is also step 6.
What?
Plugging it in because of norm CDF is step 6 too.
Yeah, but I'm going to show you something right now. Here's today's inception moment is brought to you by the TI-84 calculator.
Yes. Yeah.
Okay. Press that.
No.
Go to tests.
No.
Go to the one that says 1 proportion Z test. Because that is the one we are doing right now. 1 proportion Z test. P0. That's your hypothesis. What do you hypothesize here? That big P was 50%. What did your data say? What did your data say? We had 295 out of 737? Out of 737 people that said it. Were we checking to see if it was equal to or not equal to? Or are we looking for evidence that is less than? Or are we looking for evidence greater than? We're looking for evidence less than. Key it. Hit calculate.
What color? What is it made from? Purple. So you calculate or draw?
Calculate. And oh me, oh my, I'm shocked to see what just happened. There is a z-score of negative 5.415, which is the score we just got, with a p-value of 3.07 times 10 to the negative 8. By the way, when you do this, please don't report this as your p-value. No, I've had students, I kid you not, on their test, because we're going from step 6 to step 7, this is where you report the p-value. I've got a p-value, Mr. Wood, of 3.07.
Yes, you do.
I've got a p-value of 3.07. Never mind the fact that that's a number greater than 1, and we're talking about probabilities, and that can't even exist. But then you proceed to tell me that when you saw that you were 5 standard deviations away from what was proposed to be true, that you have a very high p-value, and there's not enough evidence because that would be a fail to reject the null hypothesis.
Interesting.
Oh, interesting. Scary thinking. Okay? It hurts me I weep and die inside a little bit every time that happens. So here's what we'll say. The p-value is approximately 0. If you'd like to report it in scientific notation, you can. Approximately 0 is good for the AP exam, and it's good for
Everybody in class.
p-value is less than or equal to 0.05. 0 is less than or equal to 0.05. That is rejecting the null hypothesis. P-value is the probability of getting a sample that rare or rarer. And in this case, it's such a rare event that I got 40% if my population was 50%. We're saying that there's a lot of evidence to say that that 50% is wrong. Okay? Step 8, write it up. We can be 95% confident that the true proportion of smokers who perceive themselves at increased risk is greater than, less than 0.5. I should say, I want to get this in there too. We can be 95% confident that there is evidence. You can add that. There is enough evidence to say that the true proportion of smokers who perceive themselves at increased risk is less than 0.5. Okay? try to get that word evidence in there, enough evidence or not enough evidence, because we're going to talk about that when we actually fail to reject. So again, it should read, I just didn't erase it, we can be 95% confident that there is enough evidence to say that the true proportion of smokers who perceive themselves to be at increased risk is less than 0.5. I guess that should be themselves. Okay? There's your top to bottom hypothesis test. Tell you what, you look pretty smart.
Oh my god.
You look smart. You are good and smart.
Oh my god.